So we're going to start looking at MOS inspection and analysis first. So in the general case of a MOS amplifier, when we look at the small signal, we would have some resistance at the gate. We'll call this big R, big G. We'd have some external resistance in the drain, big R, big D, and we'd have some external resistance in the source, big R, big S. I'm going to label big S's as dollar signs just to clarify that they are not small s's or lowercase s's. So in general, we can write voltage gain in the following terms. So this is just general. Our voltage gain, AV, is equal to some big GM times some big RT, where big GM is how well the transistor plus the surrounding resistances convert a voltage to a current, and RT is the total resistance seen at the output node. Alright, so knowing this, we would like to figure out what the impedances are looking into the terminals. So we're going to label the impedance looking into the gate as big R, little g, the impedance looking into the source as big R, little s, and the impedance looking into the drain as big R, little d. So what we need to know then are what are all these parameters equal to. So for our gate resistance, big R, little g, we know that the gate resistance should be quite high, and indeed ideally the gate resistance is equal to infinity. Big R, little s, we're going to show is equal to 1 over GM, or I should say, moreover, that you're going to show in your next homework. You're going to prove these equations. Big R, little d is equal to R sub 0, the output resistance of the transistor, times 1 plus GM times R dollar sign, or R big S. Now, what we're interested in next is finding voltage gain terms. And so we know that we have a couple of different configurations. So let's start with the common source. For a common source amplifier, we know that we're basically trying to find the voltage at the drain divided by the voltage at the gate, because our output's on the drain and our input's on the gate. This is equal to big GM times RT. And in the case of the common source amplifier, big GM is equal to minus GM divided by 1 plus GM times R dollar sign. And RT is equal to RD in parallel with R big D. Our common gate amplifier we're looking for the voltage at the drain divided by the voltage at the source. Since our input is at our source, our output's at our drain. Again, this is equal to GM times RT. But in this case, GM, big GM, is just equal to little gm. And RT is equal to the same as the common source case, R little d in parallel with R big D. Finally, we have the common drain configuration. And what we're looking for here is V source divided by V gate, our outputs on our source, our inputs on our gate. And this is equal to GM times R $, divided by 1 plus GM times R $. And remember, this is our voltage buffer. We don't get voltage gain out of this amplifier. All right, so in your homework, you're going to prove that these equations are true. We will look at the bipolar transistor equations in the next slide. All right, so we'll do the same thing for our bipolar transistor. We have some external resistance, our capital C, tied to the collector. Some external resistance, our capital E, tied to the emitter. And some external resistance, our capital B, tied to the base. Looking into each terminal, we see at the base our little b. Looking into the emitter, we see our little e. And looking into the collector, we see our little c. Note that I differentiated little c and big C with the line through the big C. So just as before, our general gain expression, AV, is going to be equal to big GM times big RT. All right, so here we know that our little b is equal to r pi. So looking into the, r pi plus 1 plus beta forward times r sub e, whatever resistance we see in the emitter. So in general, if the emitter is grounded, for instance, RE would go to 0 and we would just see R pi, which is kind of what we expect. R little c, the resistance looking into the collector, is equal to R0, the output resistance of the transistor, times 1 plus GM times R sub E, R sub big E. Now this looks very similar to the expression for the MOS device, and it should, because the devices each have 3 terminals and operate similarly from a small signal standpoint of view. The device physics is quite different, recall. So R little e is equal to 1 over GM. Now, for our common source amplifier, we have VC divided by VB, the voltage at the collector divided by the voltage at the base, is equal to GM times RT, where GM is equal to minus GM divided by 1 plus GM times R big E, and of course RT is equal to RC in parallel with big RC. Sorry, this is not common source, this is a common emitter amplifier. Alright, our next configuration would be the common base. Here we're going to have VC divided by VE, input on the emitter, output on the collector, is equal to big GM times RT, where big GM is simply equal to little gm, and RT is again equal to RC in parallel with big RC. Finally, our common collector, or emitter follower, we're looking for VE divided by VB, output on the emitter, input on the base, is equal to GM times RE divided by 1 plus GM times RE. And remember, this is also a voltage buffer. So we'll do some practice examples to prove these concepts out, but anytime that you see a common emitter, common base, common collector, common source, etc., the general solution is going to be the same. So all you have to do is recognize, is there, for instance, a resistance in the emitter of the amplifier? There is. Then we're going to figure out, which of these formulas to apply and apply them appropriately. So in the next part of the lesson, we'll look at a couple of examples.